Welcome back, ladies and gentlemen. We have now for you Dr. Julian Pittard. Dr. Pittard has worked on colliding wind binaries for 25 years. He studied originally at the University of Birmingham. He did a PhD in 1999, and then he moved to the University of Leeds. He obtained a Royal Society University Research Fellowship in 2004, of course, not 1904, and became a reader in theoretical astrophysics in 2011. He has supervised 10 PhD students and 4 postdoctoral research assistants, and he's published over 130 research papers, so he's a busy man, and he's going to talk to us now about colliding stellar winds, observations and theory.
Thank you very much, David. And thank you to the organisers for the invitation. It's a pleasure to talk to everyone here today. Continuing on with the stellar winds theme for the meeting. And this talk is going to be focused specifically on something called colliding stellar winds. This picture really sort of illustrates that fact. It's when we have two massive stars that are relatively close to each other. Usually these are a binary system. They will both have quite a strong stellar wind, and the winds will collide in between where the two stars are and heat the gas up to very high temperatures, emitting X-rays, and I'll go into some of the details about their emission in this talk. Really, it's a wonderful sort of laboratory for investigating the mass loss rates from the stars, which are poorly known in many cases, and investigating things like shock physics and particle acceleration. Okay, so just a quick overview. I'm going to spend a little bit of time talking to you about the hydrodynamics and trying to give you a bit of a flavor, really, for how these winds collide and what they do when they collide. We're going to look at some of the key parameters involved in these systems, the effect of radiative cooling, where the shock-heated gas, in some cases, is able to radiate away most of that energy very quickly. We'll look at the effect of instabilities in these systems, so the sort of hydrodynamic, Kelvin-Helmholtz, and thin shell instabilities that can arise. We'll look at what the orbit of the stars does to this wind collision region, and briefly look at radiative driving. So this is the fact that the winds that comes from the stars initially leaves the surface of the stars at a very low speed, but then is rapidly accelerated due to the huge flux of photons from the surface of the stars up until the wind reaches its so-called terminal velocity. In order to do this, we're going to look at 3D simulations. Finally, then, I'll say something very briefly about the effect of clumping in the winds and magnetic fields. And then the second part of the talk, we're going to look at some X-ray observations and the theoretical predictions of the X-ray emission. And we'll compare the two and see where we have successes and failures. And then I'll summarize and conclude at the end. So just to put it into context, first of all, what do we mean when we talk about massive stars? So a massive star, as far as I'm concerned, is a star that is more than 8 solar masses, so more than 8 times the mass of the sun. These stars are able to fuse particles inside their cores all the way up to iron and then explode as supernovae. So stars below this mass limit are not able to do that and evolve a bit differently. An 8 solar mass star will have a luminosity of about 1,500 times the luminosity of the sun. So the luminosity scales very steeply with the mass. Okay, you don't have to go up to very high masses before you see some extraordinary luminosities. And this plot here kind of highlights some of that. So I'm sure most of you are familiar with the Hertzsprung-Russell diagram. So we're plotting the luminosity of the star on the y-axis against the temperature of the star on the x-axis, and that's reversed. And most stars, if you plot them, lie on this diagonal line across the middle of the diagram, and that's known as the main sequence. This is where the stars spend most of their lifetimes merrily burning hydrogen into helium in their cores. And you can see where our sun is. That's one solar mass. It's that yellow star. Was that my pointer showing up then? It's hard for me to tell. Oh yeah, there is a pointer there. Okay, yeah, there. So that's where our sun is. So something that's got twice the mass of the sun is at this point, and then 3 times, and then 5 times. And the most massive stars are into the sort of 100 or 150 or maybe even 250 times the mass of our sun. And luminosity is at that stage of about 1 million times the luminosity of our sun. Also on the main sequence, on this plot, is how these stars evolve. So once they finish core hydrogen burning, massive stars then tend to move towards the right in this diagram. And the most massive stars, they'll move towards the right at roughly constant luminosity. They'll perhaps increase their luminosity very slightly. So our 15 solar mass star moves from off the main sequence and then becomes a blue supergiant, then a yellow supergiant, and then a red supergiant, and then ends its life at that point. A more massive star, 60 solar mass star, will again move off the main sequence, but then can display quite a number of excursions to cooler temperatures and then back to hotter temperatures, to the blue, back to the yellow or red again, and then eventually it will end up actually to the left of the main sequence as a Wolf-Rayet star. Now these particular tracks that are shown are actually very sensitive to the assumptions that we make about the mass loss of the star. So the most massive stars have very powerful stellar winds and can lose most, actually, of their mass during their lifetimes. And we have some theories for how winds, radiatively driven winds work, but unfortunately, we don't have a full, complete theory from first principles, which says if you've got a star which has this mass, it's got these properties, then we will get this mass loss rate. Okay, we don't have a complete theory for that at the moment. So what we have to do is try and measure the mass loss rate through observations. We can then compare that to our theory, tweak our parameters until the two match up, and then we can use that in our models. But the problem is our measurements may be wrong, okay, or the way we scale from one star to another may be wrong as well. So just bear in mind that there is actually, when you see these kind of evolutionary tracks, as they're known, that actually they are very uncertain. How one star will move off, it could change its luminosity a little bit more. It could change how far across the diagram it gets. And so we don't really have a good understanding of that yet. But it's actually very fundamental for how the star evolves and the impact the star has on its surroundings. Okay, so massive stars are really key agents for inputting energy into the local interstellar medium that surrounds them. And they can do this in a number of ways. First of all, they're very luminous, as we've just discussed. And because they're very hot as well, a lot of their emission is in the ultraviolet. So they have prodigious ultraviolet photons coming off them. And those ultraviolet photons, when it encounters gas, if it's absorbed, it's going to heat up the gas, perhaps from 10 Kelvin, say, if there's cold gas around, to of order 10 to the 4 Kelvin. So you may get this gas heated up by a factor of several hundred or 1,000. And that will increase the pressure of the surrounding gas. So what these stars do is transmit some of their energy into the surrounding gas. Through this method, through the ultraviolet radiation, they create things called H2 regions. These H2 regions can be highly overpressured, and the gas will want to just expand out away from the star. And this shows a region of the Carina Nebula, where we have some very hot, massive stars over on the right. And you can see that that's kind of sculpting and affecting the dense gas clouds nearby. They also have these very powerful winds, which I've mentioned. And this shows an example of a wind-blown bubble, and we've already seen some of this in Brad's talk. So this is actually the Crescent Nebula, I think. It's a Wolf-Rayet star, which has a very powerful wind, one of the most powerful winds that a massive star has, very fast, and it's sweeping up actually the earlier red supergiant wind that was emitted by the star when it was in its red supergiant phase. So that wind is moving outwards more slowly, and the Wolf-Rayet wind is catching up and sweeping it up into this beautiful nebula here. So just to give you a flavor of some numbers, what we're talking about here, a star like our sun will have a mass loss rate of about 10 to the minus 14 solar masses per year. Okay, so if our sun is going to live for of order 10 billion years, okay, it's going to lose about 10 to the minus 4 solar masses. Okay, so 0.01% of its mass due to its wind during the main sequence. So basically, the sun doesn't really lose much mass at all. Okay, the fraction of mass that's lost is very small for our sun. But if you go to some of these very massive stars, and I've highlighted here two types, a main sequence O star and the Wolf-Rayet star, we're looking at mass loss rates which are hugely stronger, and maybe 10 to the 9, a billion times stronger or faster than the mass loss rate from our sun. So these stars are more massive, so they've got more mass to lose, but they live much shorter lives, but they can actually lose a very significant fraction of their mass during their main sequence lifetimes. And these winds tend to be fast. They tend to move with speeds of order 2,000 kilometers per second. So there's a lot of kinetic energy involved in their winds, and they can have a big dynamical effect on the surrounding gas. And finally, the most massive stars, or stars above 8 solar mass, will end their life as a supernova explosion. And so this just throws out some fraction of the mass of the star into the surroundings, moving at very high speed and carrying away a lot of energy, typically 10 to the 44 joules. Okay, so that's a lot of energy being put into the interstellar medium in a very small localized region of space. And this particular image here shows a rather older supernova remnant, and you can see it swept up the surrounding gas into shelves and in this particular case, the gas has cooled, and you've kind of got these optical emitting shells. Okay, so we've got this radiation, wind, and supernova energy happening, being dumped into the local interstellar medium. This process is collectively known as feedback. So when somebody refers to as massive star feedback, they mean the effect that the ionizing photons, the winds, and the supernovae is going to have on the local interstellar medium. This is a simulation that one of my PhD students did, where we looked to see what effect feedback would have on a dense and structured gas cloud that was surrounding the stars. So this is a little bit of a toy model. There's more sophisticated models out there now. Basically, we said, okay, we know stars are born in gas clouds, so we're going to assume we've got this cloud of gas at the center of which we've got our massive stars, and then we're just going to assume that these massive stars have winds which flow out, and we're going to look at how those winds interact with the surrounding, the remaining gas in the gas cloud, and we're going to just evolve that until the stars then evolve through their different evolutionary stages, the main sequence, the red supergiant, and the Wolf-Rayet stage, and then we're going to let those stars explode as supernovae. So this particular model just assumed we had 3 massive stars that formed at the very center. They all live very slightly different lives of 5, 4.5, and 4 million years for the main sequence phase. They go through a red supergiant phase, a Wolf-Rayet phase, and then a supernova. So there will be, you'll see when I run it, the combined effect of the winds from these 3 stars, and then after about 5 million years, just under 5 million years, we'll start to see the supernovae go off as well. So let me just run that, and that will give you an idea of what these stars do. Okay, so you see the winds very rapidly blow out through the very low density material in the gas cloud. So here the orange-yellow colors is the high density gas, the blue and the black is the lowest density gas. And they kind of carve out these channels where the wind can flow quite readily out between these clumps. We see some different phases now. That's the first supernova going off, the second supernova, and the third. And basically, there isn't much left of the cloud after the stars have done their things. And so this is a good illustration, really, that early massive star feedback is important. And I think, as Brad said in his talk, this is something which has now become quite widely accepted in the astronomy community, whereas 10 years ago, people were just thinking, oh no, supernovae themselves are the only thing really that's important. I think there's now this much better understanding that winds and radiation both have an important effect to play before any supernovae go off. So that's also looking at what the stars do on local scales, but they actually can have a much bigger influence on galaxies. As Brad showed in some of his simulations, that you have these stellar clusters forming in your galaxy. The winds, the radiation, the supernova remnants then go off, and it can kind of create a very structured disk and kind of puff things up. In some extreme cases where we have things like starburst galaxies, where you have, for some reason, a big burst of star formation happen within a short period of time. This may be triggered perhaps by another galaxy passing close by. Then in such circumstances, this big burst of star formation can really put in so much energy in quite a localized region and small duration of time, that the individual bubbles from each star merge together and can drive a galactic wind. So this is an observation of M82. It's the prototypical starburst galaxy, and you see the sort of disk. It's an irregular galaxy, but you can see the disk across this image here, and then perpendicular to that, you've got this huge outflow of gas and dust as the very extreme high pressure from the starburst event in the center of the galaxy is trying to expand out. And that can have a big influence on how galaxies evolve, because you can take a lot of the interstellar medium out of the galaxy, even if that's only a temporary effect in some galaxies. It can still have a big influence. This shows, again, a little bit more of what I was saying. So this is an example of some models with stellar feedback. So this is actually quite old work now, and the particular stellar feedback model that was used in this work, I think things have moved on quite a bit since then. So it's really just as an illustration of what feedback can do, not to say that this model was perfect in every way. But what feedback tends to do is it tends to puff galaxies up. It tends to give you more of a galaxy where there's voids and lower density regions, and you see that also there's gas that tends to flow out of the galaxy. So when you have feedback, you end up with very different looking galaxies and behaving galaxies than you do without feedback. And clearly, the ones with feedback look a lot more like real galaxies. Okay, so there are some remaining puzzles with massive stars. One of the puzzles is that we have a void region in the Hertzsprung-Russell diagram where there doesn't seem to be any stars, very luminous stars, above 10 to the 6 solar luminosities in the yellow, orange, or red region. We just don't see stars in that region. This is known now as the Humphreys-Davidson limit. So you've got this sort of line here and here. So that's known as the Humphreys-Davidson limit. You don't get any stars the other side of that. And it's a real puzzle, really, because we know as stars evolve off the main sequence, they are going to want to track to the right and enter this region. So something's stopping them, okay? And we don't fully understand why. We think what happens is that the stars get close to that limit and then experience something very peculiar and undergo a period of eruptive mass loss. So this is something different from a stellar wind. It's some kind of explosion or eruption or a sudden ejection of a lot of mass from the star. The kind of typical candidate for this is Eta Carina. For those of you who've seen pictures of Eta Carina, you'll see it has this amazing nebula around it. We think there's about 20 solar masses of material in that nebula. So in the past, and this was caught actually in 1843, I think, when it went off. It was originally thought to be a supernova, but the star carried on shining. It wasn't completely destroyed. So these are now known as supernova imposters. We now have so many more examples of them. But it's still something that we don't really understand. And if we try and model the evolution of these stars, we have to put this into the code by hand. We don't have, again, a first principles understanding of how to do this and what the physics is that's driving it. So that's something to bear in mind, is when you have these tracks, at some point you have to have this eruptive mass loss or somehow increase the mass loss rate very markedly. Otherwise, you're going to go beyond the Humphreys-Davidson limit into this void, this region where we don't see any stars. So at the moment, we just do that by fudging things. We can tweak our models so that we increase the mass loss rate and stop them going into that zone. Okay, so back to colliding stellar winds. So the really nice thing about this setup is that each star is acting like an in situ probe, okay, of the other star's wind. So we can't fly out to these systems, and we can't stick a probe into the wind around these stars. But the fact that the other wind is there, that's kind of acting as some kind of probe, some kind of diagnostic of what the wind speed is and what the mass loss rate is from the other star. So they are useful in that respect. And we know most massive stars actually tend to be in binary systems. So something like 60 or 70, perhaps even 80% of the most massive stars are born as a binary. And so there will be some kind of wind collision involved in these systems. So it's something that we should try and understand. And if we can make use of this collision region in some way, if we can use it to measure the mass loss rates from these stars, then yeah, all well and good. So one thing to say is these colliding wind binaries, or CWBs for short, they're a hugely diverse population. So here I've just listed some systems which are typically studied. And I've got 5 systems there, and they're ranked in terms of the orbital periods. So some of these stars are very close together and have orbital period of a few days, and a separation between the two stars of a tenth or a couple of tenths of AU. Other ones have orbital periods of many years or tens of years, or maybe even so widely spaced that we haven't even worked out an orbit for them at all. They're just located in roughly the same region of the sky. So in those cases, the separation between the stars may be hundreds of AU. Obviously, the closer the stars are together, the higher the density of the winds when they collide. Okay, we know the density of the winds is dropping off as 1 over r squared. This is the inverse square law, again going back to Brad's talk. So if we've got the stars very close together when they collide, the gas density of the shocked gas in the collision will be high, and it will be much lower if the stars are much further apart. Now, in these systems, what you get really depends on on a couple of things. You've got the mass loss rates from both stars, you've got the wind speed from both stars, and you've got the separation between the stars. So those are your sort of 5 key parameters. In some systems, you may find that the winds are roughly similar in strength. Okay? In other systems, the wind of one star will be much stronger, maybe 100 times stronger than the other wind. And so in that case, the collision region is pushed much more closely to the star with the weaker wind, because its wind just can't hold off this much more powerful wind very, very well. In some cases, the stronger wind may completely overpower the weaker wind, and it may collide and impact directly with the companion star's surface. Okay. The other key parameter is something known as the cooling parameters. This really tells you a little bit about the physics of how rapidly the gas is going to cool. So when you have gas colliding at thousands of kilometers per second, it gets heated to extraordinary temperatures, 10 to the 7 Kelvin, 10 to the 8 Kelvin in some cases. So the gas can be even hotter than at the center of our sun. Okay, it's much lower density, but it can be hotter. This gas, in some cases, will flow out away from the system and remain hot as it does so. Okay, so it doesn't really cool very effectively. But in other systems, the gas can cool very effectively. So it gets heated up, you turn all of the kinetic energy in the wind into thermal energy, and in some cases you can then radiate away that thermal energy very efficiently. And whether you can do that or not is really encapsulated by this cooling parameter chi, which is the ratio of the cooling timescale of the gas to the timescale for the gas to flow out of the system, the so-called dynamical timescale. And you can work that out in terms of some of the fundamental parameters, so the wind velocity, the separation between the stars, and the mass loss rate. So when you have a system where chi is much greater than 1, you're going to have the hot gas remaining hot as it flows out. The cooling time is much longer than the dynamical time. It stays hot. If, on the other hand, chi is smaller than 1, you can very efficiently radiate away energy. And so your shocked gas, although it is hot as it is shocked, it then immediately cools and loses a lot of that energy. And then it will be compressed to very high density and then flow out more slowly. So we'll see that in a moment, that this has a big effect on the kind of nature of these systems. The other thing that you can have is dynamical instabilities. So there's been a number of works. So in each of these panels here, we're kind of showing the stars, the winds colliding, and in some cases you get the shocks being separated. The gas remains hot as it flows out. In other cases, the gas is able to cool quickly, and when it does that, you then tend to get this thin shell instability forming. And it forms most strongly if both winds can cool very strongly. If only one wind is cooling strongly, you still get some instability, but it's not as dramatic. And this shows, hopefully it'll work. Oh, no, oh, sorry, that's not going to work. Okay, today's first movie that didn't work. Don't worry about that, we'll move on. Okay, the other thing that is important in these systems is the fact that stars are orbiting around each other. So that, of course, will introduce a kind of a spiral into the wind collision region. So it behaves a little bit like a pinwheel as it flows out. And that spiral can be broken up if you have very strong so-called Kelvin-Helmholtz instabilities. So the figures on the right here are showing the wind color. So where you have red, we're showing one wind. Where you have sort of purple, we're showing the color of the other wind. And the intermediate color is showing where the winds are mixing. And things can stay reasonably unmixed in some circumstances, but if the shear between the two winds is above a certain critical number, then you can excite the Kelvin-Helmholtz instability very strongly, and that will then tend to do a lot more mixing. There's a few radiative effects just to say. So so the winds accelerate from the surface of the stars, and we're seeing here a profile of the wind velocity as a function of radial distance. And the star here has a radius of 10 times the radius of the sun. So the wind is starting at 0 velocity at its surface, but then accelerates away very rapidly. And within about 2 or 3 times the stellar radius, it goes up to quite close to its terminal velocity. Now, if another star is nearby, the photons from that other star will try and actually slow down that wind acceleration. Okay, so this process is known as radiative inhibition. We have another effect called radiative braking. So this can be important where you have a system where, for example, a Wolf-Rayet plus O star, where you have one star having a much stronger, more powerful wind, whereas the other star with the weaker wind actually is more luminous and has more ultraviolet photons. And then the interaction, so if you just consider the hydrodynamical forces, and if you look in the top panel here, we've got the wind coming from the Wolf-Rayet star, which is just off the grid, as shown, and it is way more powerful than the O star wind and completely overwhelms it, and so collides directly with the surface of the O star. But if we enable the O star photons to couple a little bit more strongly with this oncoming Wolf-Rayet wind, then you can actually slow down and so-called radiatively brake the oncoming Wolf-Rayet star wind. And that then allows you to have a normal ram pressure balance between the two winds in that case. So this is a kind of a more powerful, a stronger effect than radiative inhibition. And there's something called self-regulated shocks, but I won't go into that. Okay, so if we look at 3D simulations, so these are some snapshots of a simulation I did some time ago, and we're looking at slices through the orbital plane. We've got the stars marked in density and the velocity plot, and we've got the wind collision region clearly shown between the two stars, and it curves into that shape due to the orbital motion of the stars. And here we've got an example where the shocked winds cool very quickly when you account for the speed at which these winds actually interact, which is about 740 kilometers per second in this case. We have a value for chi which is below 1, which gives us very strong cooling. And if I then show you a system where we have an orbit that's slightly eccentric, so we've got an eccentricity of 0.36. So in this case, the separation between the stars is varying by roughly a factor of 2. So on the left plot, we've got the stars as they pass through their closest approach, and then on the right panel, we've got the stars at their widest separation. And you can see that the nature of the wind collision region is quite different between these cases. Close approach, we've got very strong cooling, so we've got a very dense and thin collision region, whereas when the stars are at their maximum separation, there's a bit more room for the stars, for the winds to accelerate before they collide, and this allows the cooling parameter to be greater than 1, and the gas can flow out while remaining hot. And this actually shows a movie of this process. So we've got all of the radiative driving forces being calculated, we've got gravity being calculated, and obviously the orbital motion of the stars. And what this simulation showed is the fact that there's a sort of a time lag that's introduced by the orbital motion and the radiative cooling. And so you can get these dense clumps of gas even at phase 0.5 at apastron, when the stars are at their maximum separation, because they're left over from what happened at periastron a few days previously. Here's a simulation of another system. It's got an 860-day orbit. So because these stars are more widely separated, their winds always collide, and the gas always remains hot throughout the entire orbit in this case. And then we have a system where we have a Wolf-Rayet wind and an O9 companion star with a relatively weaker wind. So you can see the more powerful wind is bending the wind collision region closer to the O star. And this particular simulation was run where we assumed the wind is flowing off the stars at its terminal velocity. And in that case, we can keep a wind balance throughout the entire orbit, and the post-shock plasma remains hot. The shocked O9 wind doesn't significantly cool. Now, if we do a more realistic simulation where we've got the radiative driving, we now see that the winds collide before they reach their terminal velocities, and this means the post-shock plasma is cooler and denser. The shocked O wind now radiates strongly, so you get much thinner, denser gas formed, and crucially, the wind collision region collapses onto the O star, onto the surface of the O star, as the star moves through its closest approach, and then it's pushed off the surface of the O star as the stars separate. So the dynamics are quite different if you include this radiative driving of the winds. And this just shows a zoom on this. So we're seeing the two stars in their orbit. And you can see that there's these dynamical instabilities play a role in when it collapses onto the other star. So if I can play that again. So if we look at the apex of the wind collision region, it starts to cool, and then you get these violent instabilities, and one part of it will touch the O star surface, and then the whole thing is then just collapses onto the O star until the stars separate enough that the O star wind can manage to re-establish itself. Here's a simulation of Eta Carina. So one of the most famous stars, I've already mentioned, Eta Carina, is now believed to be a binary system. It was discovered about 20, 25 years or so ago that there seemed to be a clockwork periodicity to this system, which is, of course, best explained by having a companion star. And this system is very unusual because we've got the wind from the stronger wind is an LBV wind, so it's a relatively slow wind, and that's colliding with a much faster companion wind. And the orbital period of this system is about 5.5 years, and the eccentricity is extremely high, 0.9. So there's about a factor of 20 variation between the wider separation and the closer separation between the stars. So there's a big change in the physical conditions of the wind collision region as the stars go around. WR140 has some similar characteristics to Eta Carina. It's got a similar period, 7 or 8 years in this case, and a similar eccentricity. But in this case, the stronger wind has a high speed. It's a Wolf-Rayet wind in this case. So doing these simulations gives us a flavor, an idea of what's going on. But the real world, of course, is always a bit more messy. We know these winds are very clumpy. So how does that affect things? Well, if the gas doesn't cool very quickly, then essentially the clumps are just destroyed quite easily, rapidly within this collision region. It's very turbulent. Perhaps the clumps make it even more turbulent. This might have some implications for things like particle acceleration. But at least in some systems, it seems clumps aren't really going to do much. In fact, the wind collision region really kind of smooths out the fact that you've got these clumps. The other thing you might wonder about is, what about magnetic fields? It turns out that in colliding wind binaries, magnetic fields are probably not very important for most systems. Just the kinetic energy in the winds is enough to drag out the field lines into pretty sort of radial configurations. And so there isn't really a big effect on the shape or the dynamics of the wind collision region. Okay, we'll now have a look at some X-ray observations and challenges. So I'm just going to go through sort of 3 sets of systems. So first of all, we'll look at what should be the simplest systems, the adiabatic systems. These are the systems where the gas remains hot. It doesn't cool effectively. It flows out of the system while it's hot. And theory tells us that the X-ray luminosity from these systems should scale as 1 over the orbital separation. So we can test that now. Okay, so if we look at these systems with eccentric orbits and we point an X-ray telescope at these systems, then we're hoping to see that the X-ray luminosity will scale with 1 over the orbital separation. So there's 2 systems where we can do that, or where that's been done. We're then going to look at intermediate systems where one or the other wind is perhaps suffering some degree of cooling, or perhaps suffers cooling in parts of the orbit, even if it remains roughly adiabatic most other times. These systems don't behave very well. And then I'll also mention a radiative system, so a system where the stars are close together, winds are very dense, it should cool very rapidly, and in that case, we expect the X-ray luminosity just to scale with the mass loss rate and not have a dependence on the orbital separation, and we'll see that system doesn't behave well at all. So, starting off then with the adiabatic systems, as I said, we expect the X-ray luminosity to be proportional to 1 over the stellar separation, dSep. Okay, if the system is adiabatic, but if chi is less than 1, we expect Lx to be independent of the orbital separation. So, for some systems like SIG-OB2 number 9, which is a very adiabatic system, we do see this behavior, so that's good. Okay, we're happy with that. So what I'm showing here in this top figure is an X-ray spectrum. So you're all familiar, I hope, with optical spectra. Okay, so where you're looking at the how bright something is in the red compared to the blue. Okay, you'll all be you know that there's a wide range of electromagnetic radiation okay? And you know the electromagnetic spectrum extends down to the radio at one end and up to the gamma ray region at the other. Well, these systems, because the collision region is so hot, is producing a lot of X-rays. So if we want to learn about these, then X-rays are the best thing to look at. We use X-ray telescopes in space because our atmosphere blocks the X-rays coming down towards us, so we can't use detectors on the ground. So these are telescopes which are in space, orbiting around the Earth, and there's a number of really good X-ray telescopes. The spectrum that I'm showing here is plotting counts per second per keV. Okay, that's just the number of X-ray photons versus the energy of the photons. So we've got a low energy X-ray photon on the left and high energy X-ray photons on the right. And we've got two spectra. We've got a red spectrum and a black spectrum, and they're taken at different orbital phases for this system. So it's a highly eccentric system. So at one part of the orbit, the X-ray emission is brighter than at the other part. Okay, and it very nicely matches our theoretical expectations. It's about 4 times brighter in X-rays. The red spectrum is about 4 times higher flux than the black spectrum, which is in good agreement with what we expect. So the problem now comes from when we actually try and compare that to our models, okay? Because we can't, as well as just looking at the difference between these observations, we can actually try and use our models to make predictions about what the X-ray spectrum should look like and how bright it should be, okay? And that's shown here in this bottom panel. So we've got the brightness of our X-ray emission versus orbital phase. So orbital phase 1 is periastron, when the stars are closest together, so that's when the emission's highest. So that's why it peaks, and then it drops off following this 1/d law towards orbital phase 1.5 or 0.5, which is apastron, the wider separation of the stars. And so we see that nice 1/d variation. But the problem is the data is shown here in the squares at the bottom, these green squares. And in order to match that data, we can only do that if we reduce our mass loss rates by a factor of 10 in our models. If we plug in the mass loss rates that we expect for these stars, then our emission is 100 times too bright. Okay, so it scales as the mass loss rate squared. So that's really quite uncomfortable, okay? We know we're not going to have our mass loss rates measured or pinned down to within better than a factor of 2 or 3, but a factor of 10 is really quite uncomfortable. That makes a big difference to how these stars evolve and the effect they have on the interstellar medium. So this is where it's a really, really sobering thing at this point. How can that be so wrong? And I'll mention something at the end of the talk. We've also got problems with some other systems. So this is an X-ray light curve for WR140. It shows, again, a lovely 1/d behavior, which is this kind of curved rise. There's a very sharp dip as one of the stars with the thicker wind gets in front and absorbs some of the X-rays. So I'll not concentrate on that. We're just looking at the rise and fall. And if we look at some particular phases of the X-ray emission, and I've shown here the orbit. So we've got the Wolf-Rayet star moving relative to the O star, and it's coming towards its closest approach, periastron passage, and then moving away. And if we plot the emission that we observe, the brightness of the X-rays versus the separation of the stars, we see that in the right panel, And if this is behaving properly, then again, it should just be a 1 over d, which gives us a nice straight linear line. So things work okay between A and B. We get quite a nice linear line, but then it goes horribly wrong between B, C, and D. In fact, the X-ray emission actually turns over and gets less bright as the stars get closer together, which is not something we expect at all. One way, something that might influence this is the fact that as the stars get closer together, they're moving into the acceleration zone of their winds. Okay, so we're actually getting to the point where the velocity of the winds as they come together is changing, it's reducing because the stars are getting into the acceleration zones. And that could turn things over a little bit, but still it's not something that we're very comfortable with at the moment. It seems to be we need to do some more work there. WR22 is also a big problem. We've got 2 possible orbits for this system, so that just shows the kind of uncertainty that's involved with this. We've got count rates for these systems, for the X-ray emission, and what you see.
3 minutes, Julian.
Okay, great. What you see here is the hard X-ray emission, that the very most energetic X-rays are not varying at all. That's roughly flat, that top panel on the right. So that's something which is not behaving as it should. Okay, we're not seeing that 1 over d variation. And here we look at the actual spectra. And again, you see the hard emission. If you look at the spectrum between 2 and 5 keV, it's really not changing much in these different pointings. So perhaps there's some extra things going on. Perhaps the wind collision region's collapsing down onto the other star, and this affecting and making invalid this 1 over d scaling. And again, we've got another big problem with the X-ray emission being hugely overestimated by a factor of 100 or so. So again, that's a very uncomfortable change to the mass loss rates we'd have to make. Gamma Velorum, again, another problem system, because when we look at the 2 spectra here, shown on the right, again, the high energy X-rays are roughly constant. There's no significant change in the emission at high energies, whereas we do expect to see something. And then for the irradiative systems, such as WR21A, here we expect the winds to cool rapidly, so we don't expect to see a 1 over d variation, but we actually do. So that's the wrong way around. And that's a real puzzle. We clearly need to do a lot more work here. So there's 2 ways out of this, and I know I'm pressed for time now, so just very, very quickly talk about them. There's something called the radiative overstability, which affects shocks. So that can affect the X-ray flux as a function of time. But more importantly, we may have some suppression of X-rays going on due to instabilities. And this was a paper worked out by Key and collaborators, and they found that once you get very strong cooling, then the oscillations of the shocks produce very oblique shocks instead of a head-on collision. The gas tends to collide more at an oblique angle, and that can significantly reduce the X-ray emission. And they find that when that happens, it reduces by about a factor of 50. So you can see from the top line down to the bottom line, it's dropping by a factor of 50. And they did some more simulations of that. And you see the blue points towards the right are about 50 times lower than the radiative theory would make you predict. So that can get you most of the way to some of the discrepancies we see when we compare models to observations. Another difference, or way out perhaps, is that a lot of the energy may actually be going into accelerating particles. And this shows radio emission from WR146, which is a very bright colliding wind binary in the radio. The southern source is the Wolf-Rayet star. The northern source is the O star. And the VLA contours in blue are showing the emission from the two stellar winds. And then the VLBA contours in red are showing the non-thermal emission from the wind collision region. So that all looks as we expect for a colliding wind binary. So the key question is, well, given that there's this non-thermal radiation and particle acceleration going on, just how much energy, what fraction of the wind power is going into accelerating particles? Because however much you put into that gives you a big, a reduction, a corresponding reduction in the energy available for the thermal X-ray emission. So that could be another way of solving that. And I'll skip that, and we'll just go on to the final slide. So I hope I've shown you. Colliding wind binaries are really interesting systems. They're very diverse. They're very useful laboratories for investigating massive stars and their stellar wind properties, the physics of high Mach number shocks and particle acceleration. Highly eccentric systems are just the bee's knees, because we can use the changing separation as the ultimate sort of in situ probe. And our understanding of these systems has come a long way in recent years, but we're still having some puzzles to work out. We've got much lower X-ray emission predicted than expected for some of these systems. We have peculiar scalings with some of them. We have a lack of variability in some of them. And we have variability in some of them where we expect them to show no variability. So puzzles all around. And the two kind of unanswered questions are instabilities suppressing the X-rays? Would that help solve some of these problems? And is significant energy going into accelerating non-thermal particles? Would that solve, again, some of the other problems with these systems? So I hope that's given you a snapshot of the sort of current research that's going on with these systems. So,
thank you very much, Julian. I'll just take one question. I think we've only got time for if anybody wants to ask one.
You're going to have to run up.
I'll give our youngest member the last word today.
So, my question is, NASA has recently recorded the sound of the sun using the solar winds. So, what would if they mapped out the sound of the solar winds colliding, what would it sound like?
Ooh.
You didn't expect that one, did you?
No, that's a very good question. You put me on the spot there. Okay, I'm not entirely sure how to start with answering this. I know our sun is oscillating. It's ringing like a bell, and people use that to work out the internal structure of the star, of our sun. And this is something that we can also do for other stars. So for our sun, it's called helioseismology. For other stars, this is the field of astroseismology. I don't think you can really do anything really with sound for the colliding winds, but I think some of these stars are pulsating, okay, and that's partly due to sound waves within these stars. And we believe in many cases that can have an effect on the wind properties coming off the star. You know, at some level, there is going to be some variation in the strength of these winds due to pulsations in the stars themselves. And that will have some effect on the nature of the wind collision region, how much X-rays perhaps are generated. But I'm not sure we could easily measure that. I don't think we're quite that sophisticated yet. As you can see, we already have a lot of problems, even with more simple things.
Well, I think that's quite an appropriate question since we're in the School of Music today. I'm sure you get a lot of higher harmonics from that collision.
Yeah.
Well, I've been ordered that we have to end the meeting now. So thank you very much, Julian. Again, we had a question on YouTube stream from Jeremy Shears, director of the variable star section of the BAA, but I'm not going to give that now. And Theo Lawson says, "Great talk, Julian."
Oh, yeah,
so there's a few people watching. We've had about 15 people watching on the YouTube as well. So thank you very much, Julian.
Thank you.
So, I'll just remind you that the next BAA meeting will be May the 25th at the Institute of Physics in London. That'll be at 1700 in the evening, and we've got talks from Mike Fawkes on Saturn, and one about eclipsing a binary WCPI, and we've got Sky Notes as well. I'll just thank some people. I have to thank Dan Merrick, who's head of music, for agreeing to use of this building. I have to thank Jack up the top for making an excellent job of the AV, and flawless, really, and doing the broadcast, managing the broadcast for us. Sarah for refreshments. Also, Andy Wilson at the BAA for his work in helping to organise the meeting. Of course, all the speakers, including Rod and Dave from Leeds Astronomical Society, organising their participation in the meeting. And most of all, to Hazel Collett for all the work she has done on organising the meeting. Thank you very much. And also Mary Louise here for her help as well. So, safe journey home, everybody, and good night.